What's up, everybody? It's Dan from SageMathTutoring.com here with another video for my friend who's taken the Contemporary Mathematics test for Excelsior College. And these are all the things she needs to know. So I want to do a brief, well, it's probably not going to be brief actually, but I want to do a video talking about these things. It's not really the same as doing problems and providing examples. Doing problems and providing examples is in another video that I did. So there should be some, I think there's 2 other videos for the Contemporary Mathematics test. So this isn't really going to be about providing examples, but it is going to be about talking about the general concepts. All right, so hopefully this is helpful. So let's take a look at Part 1A, thinking critically, inductive reasoning, deductive reasoning, connective reasoning. Okay, so basically, with this stuff, what the teachers or the test givers, creators want you to know, in general, is the difference between inductive, deductive, and connective. Now, inductive is basically when, basically you make observations, and once you reach enough observations, then you can form a conclusion about the world. So you, in a sense, make a generalization based on your observations. So, for example, maybe you have observed that the sun rises in the east, like every day, a lot. Many times, I'll put in parentheses, many times. And because you've observed that so many times, you make the conclusion that the sun always rises in the east. All right. Once again, that is called inductive reasoning. And that's how that works. This process is called generalization. I definitely know everybody does generalization. It can, of course, go too far, but generalization is required to survive. Okay, you have to make generalizations about the world. But anyway, that's inductive reasoning. That's how that works. And when you look at deductive reasoning, which is the next thing, deductive reasoning, that's sometimes called the top-down approach. Aristotle either created it or unveiled it or revealed it, So deductive reasoning is quite old because, Aristotle, that was a long time ago, ancient Greece. So deductive reasoning is top-down, where you start with premises. Okay, you start with premises. And then you have a conclusion after the premises. All right, I'll just write CONCL. And the most classic example is all men are mortal. Socrates was a man. Very famous example of deductive reasoning. Therefore, Socrates was mortal. All right, so once again, deductive reasoning brings you from premises, so you have these assumptions, right? And, of course, you have to just assume that these are true, and then it logically follows with a conclusion based on the assumptions. All right. There's a lot more to say about that, talking about the difference between valid and invalid arguments and so on. But I'm not seeing, based on the practice test from the Contemporary Math test practice test, that you really need to get too deep into this. All right. So I'm going to just move on for now. So let's take a look at connective reasoning. My student is actually really good at connective reasoning. I'm going to actually just use an asterisk, I think. Sometimes I fly by the seat of my pants with these videos. I just jump in without much of a plan and I think the new plan is to use asterisks. So connective reasoning, that's basically when you assign a letter to various statements. For example, P could be like, it is raining. All right. Q could be something like, I am going to work. Okay. And basically, once you've labeled various statements with a P and a Q, you have these other symbols that can really help symbolize statements and larger statements. So, for example, this means and. This right side up V means or. And sometimes it's this, but also sometimes it's that. That means not. So basically, imagine we were challenging ourselves to write, it is not raining. And I am going to work. Imagine we were challenging ourselves to do that. Well, what you would write is you'd focus here. So it is not raining would be not P. Because P is it is raining, not P is it is not raining. The word and would be written as this symbol. And I am going to work is already represented by Q. So, boom. And to sort of sum it up, it would be this, as the answer would be not P, upside down V, Q. So that is connective reasoning. There's all these interesting symbols. Once again, my student has demonstrated competence in that area, so I'm very happy about that. Anyway, moving on. Okay, so moving on to the next thing they mentioned, problem solving techniques, Polia's 4 steps. Okay, best way to remember this, in my opinion, is U, P, S, check. And U stands for understand the problem. And this is really applicable to word problems in particular. P is plan. You got to make a plan, maybe use some sort of mathematical model. S stands for solve. And then check means check to make sure that you got the right answer. So for example, if I had some word problem that was like, we have filled up 3/12 of the pool, and also we filled up, maybe, let's see, 1/2 of the pool. How much more of the pool do we need to fill? How much more do we need? So, very brief, sort of dinky little rudimentary word problem. Anyway, first step, understand it. It's like, okay, understanding really means, take into account what's relevant, take into account what's not relevant, ignore anything that's not relevant. For example, if it says something like, Joe has filled up 3/12 plus 1/2 of the pool, do you really need to know his name? No. So completely ignore the fact that his name is Joe. It doesn't matter. What's pertinent is the fact that there's 3/12 of the pool filled. Also, another 1/2 of the pool got filled, and we want to know how much more we need. So we want to understand the problem, right? Plan often is a matter of finding a model that works. For example, some people like to actually draw this kind of scenario where it's like, 3/12 right here, maybe 1/2 is right here, not drawn to scale, and then a big fat question mark right there, we could plan by, maybe modeling it, getting a sense of what's needed. For example, we can kind of see that it's going to be 3/12 plus 1/2, right? So you want to plan your strategy, and then finally you want to actually solve it. For example, solving it by saying, okay, well, 3/12 plus 1/2. Now I'm going to turn 1/2 into 6/12 to get that common denominator, and that is 9/12. The whole thing would be 1, right? The whole thing would be 1. So we could say that 1 minus 9/12, and by calculating that, that would end up being 3/12, also known as 1/4. We're just going to leave it alone because, once again, I don't want to focus too much on practice problems. That has more to do with understanding Pauli has 4 steps and the concepts. So we just solved it. 3/12, also known as 1/4. You should reduce that. And then you're going to want to check. Well, how would you check? Well, you would add 3/12 plus 1/2 plus another 3/12, and you would check to see if you get 1. Okay, so you want to check, in other words. All right, so that's the Pauli has 4 steps: understand, plan, solve, check, UPS, check. Okay, moving on to estimation. And estimation, I'm going to assume that they mean, rounding things off to make things easy for yourself to get a general ballpark idea of the answer. So, for example, if we had these, well, you could certainly perform an estimation and turn 550 into 600 and 933 into 900, and then you could add those, and then that's a very easy calculation. That is most definitely 1500, also known as 1500. Keep in mind that this 5, if it's 5 or above, then it bumps up the, in this case would be the hundreds position, you bumps it up to a 6, and anything less than 5 rounds down, so 3 is less than 5, therefore it rounds down to 900. The same could be applied to multiplication, like 36 times 53, something like that. I do believe my student could definitely do this, but a nice way to round it would be to turn that into 40, multiply that times 50, and 40 times 50, well, 4 times 5 is 20, so you could write that. And you also know that there's these extra 2 zeros, which results in tacking on the extra 2 zeros right there, giving us 2,000. So 2,000, 36 times 53, it's about 2,000, not exactly 2,000, but in that ballpark. Okay, so looking at the next item mentioned, they say mathematical model. So that's actually fairly, I'd say, somewhat open-ended and vague, but really in general, mathematical model is a description of really a system, a real-world system, we could say. It's a description of a real-world system. Description. Using math language. And that means variables, yada, yada, yada. All right. So, for example, imagine we had something like a box that was 3 times, that had a, we'll say the width. The width is 3 times the height, and the length is 2 times the height. And imagine that that's our box. Well, you might know that boxes are such that they most certainly have a width, they most certainly have a length, and they most certainly have a height. But a good mathematical model to describe this situation would be to redraw it only with a single variable represented. So the length is 2 times the height, the width is 3 times the height, so it seems like the height is kind of a big deal. So we are going to write h. H is, in a sense, the star of the show. And the width, according to this, is 3 times h, so you could do that. And the length, of course, is 2 times h. So we could do that. And I would say that this is a great model to describe our quote-unquote real-world scenario. And mathematical models could be used in all kinds of fields like physics, biology, chemistry, and so on. But I'd say that this is a good model for our situation, and in that, seeing as how it's the case that the volume of any rectangular prism like this is going to be length times width times height. Well, guess what? The volume of this thing is going to be length times width times height, but our length in this case is 2h, our width is 3h, and our height is h. So that would be 2h times 3h times h itself, which becomes 6h cubed. So that is a beautiful equation that would represent the volume of our special box. Okay, this is a quick example of a mathematical model based on a scenario that is described to us, and we're translating it into math language. All right, so hopefully that makes sense. Okay, so now we move into the realm of statistics. First concept is sampling, random samples. Random samples, it just basically means you have a population of something. I don't know. Let's say that this is... you know what? I'm going to draw a nice hat. An upside down top hat. Upside down top hat. Right there. Yay, there it is. And inside, we have people who threw in like raffle tickets or whatever. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So imagine we want to pull a sample of 3. And in fact, we're going to pull a random sample of 3. So that basically means that you are randomly pulling out a smaller sample from a larger population. All right. And I will circle these. And there's ways of doing it. For example, in the case of the top hat scenario, maybe you would just have somebody, without looking at the numbers, reach in the top hat and pull out 3 numbers, right? Imagine it's 2, 10, and 7. Well, those would be the random samples in that case. Now, obviously, it's not always going to be a top hat raffle ticket type scenario. There's all kinds of situations where we could randomly sample a population, but the random sample, you want to be clear on how many you're sampling, and you want to get clear about what your population is, and you want to make sure that you're doing it randomly. We made sure that we were doing it randomly by reaching into the hat without thinking or without looking, and in other cases, you might want to use a computer to generate random samples and things like that. But the bottom line is the sample is random and therefore unbiased, hopefully. Okay, so frequency distribution. Okay, frequency distributions is a great way to summarize data. All right, now data is information that you are observing. So, for example, imagine we have like a daily demand for an iPhone. We'll make that an iPhone. And the daily demand is such that on day 1, let's say you run a store and you're selling iPhones, and on day 1 there's a demand for 1 iPhone. For day 2, there's a demand for 2 iPhones, day 3, and so on. And this kind of lists all the demands on each day. Okay, so that's the list of demands for each day. On day 1, they demanded 1. On day 2, they demanded 2. On day 3, they demanded 1. On day 4, they demanded 0, and so on. And what you could do is you could write a frequency distribution to summarize what just happened, to summarize your observations, And you could put the demand on the left and the frequency on the right. And just get clear, you know, what's the range of demand? It went from 0, and the highest value is 4 represented. So you could list that in order. That's a nice way of doing it. And then count up, you know, how many times did 0 show up? It showed up 1, 2, 3. So that's going to be a 3. How many times did 1 show up? 1, 2, 3, 4, 5. So that's going to be a 5. How many times did 2 show up? We have 1, 2, 3, 4 right there. And how many times did 3 show up? We would soon discover it's 2. How many times did 4 show up? We would discover that it's 1. And maybe to make this a little more organized, we could do something like that. But this is a beautiful frequency distribution that really shows what just happened over here. Clearly we could see that the most popular demand is for one iPhone. Okay, there were literally 5 days where people demanded one iPhone, so that's the most common scenario. And there was only 1 day where people demanded 4 iPhones, which I guess makes sense because, 4 iPhones, that's a lot compared to the rest of it. So maybe that's a little bit rare. But anyway, that's an intro to frequency distributions. Okay, so let's look at histograms now. Histograms are very similar to like a bar graph. Maybe you could even say it's a kind of bar graph. My student at home, you probably remember bar graphs look like this. However, histograms are a little different in that the bars are always going to be, right next to each other. All right, so that right there is a histogram. Let's see. What else could I say about it? Well, I could definitely say that when it comes to a histogram, there's often a range of values represented down here. So, for example, maybe from 0 to 9, from 10 to 19, and from 20 to 29. Okay, and, of course, there's going to be a range of values here. Maybe 1, 2, and 3. And maybe this could be perhaps this could be a scenario where you have a whole bunch of people in a restaurant and you're analyzing their ages, and according to the information, there is only one person that is between the ages of 0 and 9. There are 2 people that are between the ages of 10 and 19. And then there are, let's just call this 3. There are 3 people that are between the ages of 20 and 29. All right, so that is a way of thinking about histograms. So hopefully that makes sense. And that's just a way of displaying data. Okay, measures of central tendency. So my students definitely pretty good at this, I've noticed. The mean, right here, I'll do the asterisk method. Mean, that is the average, right? So if we wanted the mean of these numbers, well, you would have to add them and divide by the amount of numbers that you're dealing with, which is, of course, 3. And you would take it from there. All right, so let's actually do it. 35 plus 60 is 95 plus 72. So 90 plus 70 is 160, and the 5 plus 2 is 7. So that's going to be 167 divided by 3. Not sure if that's going to work out to a nice number. Let's see. Is this divisible by 3? It is not. But let's see. 3 into 16 is 5. And then 3 into 17 is yet another 5. And that would give you, it's 55 with a remainder of 2. And therefore, we could say that's the average. Now, you might want to do a decimal. You could always bust out the calculator if you need to. But that is essentially the average right there. So that's the mean. That's how you do mean. What about median? So there's the concept of median, which basically means the middle number after you list the numbers in order. So for example, if I had these numbers, the first order of business would be to write them in order. And 1 comes first, then it's 2, then 10, 14, 37. So we're going to rewrite it in order. And once we've done that, you then look for the middle number. Now, I've seen people do an interesting method, which I kind of like actually, where they narrow it down by taking away the numbers on the outside, and then they go in, and then whatever's left over is the actual median. And as many of you who are watching know, unfortunately, it can get a little bit more complicated when you have an even amount of numbers. So for example, if we had 3, 1, 3, 5, 10, and 12, and 14, you could do that method where it's like, okay, chip away these, but now we're left with 2 in the middle. Whenever that's the case, you just take the average of the 2 and you will be fine. All right, that's the median. That will give you the median. Once again, be sure to list the numbers in order first before you do any of that. So that is the median. It's really as simple as that. You might have to, just be careful with the order of the numbers and all that stuff. Okay, so the mode. The mode is the number that shows up the most. So for example, if we had something like this, then the mode would be 5 because it shows up twice. If we had something like this, then there would be no mode because there is no number that shows up more than once. And if we had something like this, then the mode would be plural because we have 2 modes, 2 and 3, because 2 shows up twice and 3 shows up twice. All right, so the mode is the number that shows up the most, and 2 and 3 would work in this case. All right, so I brought this in right here to just correlate it with this, because this says measures of dispersion, and these are all the measures of dispersion. We're actually going to go to the next slide and talk about all this stuff. Okay, so range. Range is the difference between the largest number in a list and the smallest number in a list. And again, helps maybe to list them in order first. And, take note of the largest, take note of the smallest. Now, you don't have to list it in order, but it might be helpful. And then you just subtract the smallest from the largest, and clearly that would, in this case, be 74 once you've done that. All right, so that's that one. Okay, let's see. So, variance. Well, I think the variance and the standard deviation should be explained together. I have noticed on various practice tests that this relationship is really important to understand because it is the case that the standard deviation, often denoted by the sigma, is really the square root of the variation. So this is the standard deviation, and the variance could be denoted as sigma squared. All right, so first and foremost, I want my student to understand standard deviation is sigma, maybe some number, right? Sigma stands for whatever that number is, and variance is sigma squared. So there is this relationship. So in other words, if you have the standard deviation, it's very easy to find the variance. You just square the standard deviation. If you have the variance, it's very easy to find the standard deviation. All you have to do is take the square root of that, and you're going to end up with that. All right, so that's the first thing to take note of. I'm going to go ahead and just say, why don't we just find the standard deviation right now, and of a certain group of numbers. And I'll kind of explain that. And I want my student to keep in mind that, if you have the standard deviation, you can easily have the variance, like I just said, and so on. Or you go back and forth between the two. And first of all, it's good to know, okay, what is the standard deviation? And basically, the standard deviation is a way of finding how much each data item differs from the mean. All right, so imagine we have all these data items. We'll call it 778, just a bunch of random numbers. 472. 147, 106, 82, and we want to find out how much these numbers differ from the mean of this set on average. So the first thing you want to do is find the mean. So the mean is found by adding them all together and dividing by 5. Now if you added them all together, you would get 1,585, and if you divided by 5 after that, you would get 317. So that right there is the mean, okay? And again, what we want to do is find out how much each of these numbers differ from the mean on average. And the best way to do that is as follows. Basically what you have to do is, sometimes it's good to make a chart actually. So you could always list these numbers like this, like down a column. All right, 147, 106, and 82, and that could be the first column, and we could call that the data. And then you figure out what the quote-unquote deviation is, and that's going to be the data minus the mean. All right, minus the mean. And that would be 778 minus 317, and so on. So I'm going to fill this out right now. So in each of these little rows, we're subtracting the mean, and this would equal 461. This one would equal 155. This one would be 170, or negative 170 actually. This would be negative 211, and this would be negative 235. And then what you would want to do at that point is take the average of the squares of these. So you're going to want to square these. Mathematicians like to square these because we want the negatives to become positive. So what we do is we end up squaring these numbers. So what we're going to end up with is this. We're going to have 461 squared plus 155 squared plus negative 170 squared plus negative 211 squared plus negative 235 squared. And that's the big picture of what we're going to do, at least in the numerator. And then once we square all that stuff, we're going to divide it by the amount of numbers that you're dealing with minus 1. All right, so you're going to divide it by the amount of numbers that you're dealing with minus 1. So we have 1, 2, 3, 4, 5. So we're going to divide the whole thing by 4. And let's get the big picture. After that, we're going to take the square root of this whole thing. That gives you the standard deviation. Okay? And that's how you would find this. I have yet to see a practice test for my students that required her to actually perform this whole calculation. All right, now this is something that I know that she could do in her calculator. Do all the squaring first, plug this in, use parentheses if you have a graphing calculator, add it, divide it by 4, and then take the square root of the result. That's a good way to go. Or you could just take the square root of everything, put parentheses around this, etc., etc. If you know how to use a graphing calculator and you're proficient at it, you could actually kind of bang it out in one shot. But anyway, when you take the square root, it ends up being the standard deviation. If you were to not take the square root, guess what you would have? The variance. So in other words, the variance, like this is the standard deviation, but the variance would be everything I just said only without the square root symbol. Okay? And again, you would have to calculate all of this stuff. All right, so that is a general idea of what is required for the variance. This right here is the variance, and if you were to take the square root of it, that would be the standard deviation. All right, fairly lengthy process. Anyway, let's move on. All right, so the next concept is, let's see, percentiles. So the first question is, what is a percentile? Okay, so a percentile is a way of measuring data such that you list numbers in order, and for example, if you want to say, let's see, if you want to say something like the 80th percentile, essentially what that means is that, like if you say the 80th percentile of data, that is the value such that 80% of the numbers fall at or below that value, and the rest fall at or above that value. All right, so if you say something like the 80th percentile, and you have a list of numbers, like here's a whole bunch of numbers. If you say the 80th percentile, that is the number that is such that 80% of the numbers fall below it, and the rest fall above it. All right, so that's a way of thinking about it. I think I will show a brief example real quick. At the end of the day, finding percentiles is a three-step process. So let's say we have the following numbers where it's like 3, 1, 2, 10, 11, 14, and 17. Now that is 1, 2, 3, 4, 5, 6, 7 numbers. And the first order of business is to write these in order. So 1 comes first, 2 comes next, 3 comes next. Let's see, 11. Actually, that would be 10. We have 10. We have 11, and then we have 14. And finally, we have 17. And the three-step process to find the percentile is, first of all, get clear on what percentile they're looking for. Let's say it's the 30th percentile. And what you want to do in this case is you want to use the following formula. And that formula is L equals P over 100 times N. Now let's get clear about what these mean. So N is the amount of numbers that you're dealing with, okay? P is the actual percent number. L is what's called the locator. And let's do it right now. So we want to find the locator. So that's going to be L equals 30 over 100 times the amount of numbers that you are dealing with. In this case, it's 7 because we have 1, 2, 3, 4, 5, 6, 7. So if I was to plug that into the calculator, I would end up getting 2.1. So L equals 2.1. Now that right there is what is called the locator. Now here's the deal. If you end up with a decimal number like 2.1, you then round it up. Okay, so this would get rounded up to 3. All right? So that's the rule of thumb. If you end up with a decimal, you round it up to 3. And that tells you how many spaces to move in order to find your locator. And that's 1, 2, and 3. And this, therefore, if we were to ask what the 30th percentile is in this list of numbers, it would definitely be 3. 3 is the 30th percentile. Now, had we gotten a whole number, like let's say we went through all these motions and we ended up with something called L equals, let's say, 5, okay? Had we gotten a whole number, what that means is you have to take the 5th one, which is 1, 2, 3, 4, and 5. We would have to take this one, the 5th one, and the 6th one, and we would have had to find the average of these two. And that number, whatever the average is of 11 and 14, that would be the actual percentile, okay? So the average of 11 and 14, by the way, is, let's see, that's going to be 12.5. So 12.5 would end up being the percentile, all right? So once again, you take note of what percentile, percentage you're looking for, and then you use this formula. And then if you get a decimal, you round it up. That gives you how many spaces over, and that number itself is the percentile, the 30th percentile in this case. Let's say we ended up, trying to find another percentile, and we ended up with a whole number, L equals 5. Well then, since this is a whole number, you'd have to take the average of the 5th position and the 6th position, and whatever number you get, that ends up being the percentile. Okay, hopefully that makes sense. Okay, so looking at quartiles now. Quartiles is really just a special version of what we were just talking about, where the stars of the show when it comes to quartiles are the 25th percentile, the 50th percentile, the 75th percentile, and this is called the first quartile, this is the second quartile, this is the third quartile. So imagine you had a whole list of numbers and somebody wanted to know what the first quartile is. Well, that's basically the number that is at the 25th percentile, and the same thing goes for the second quartile, and the same thing goes for the third quartile. So just know that quartiles is pretty much the same thing as a percentile problem. You would still want to use this, where it's like P over 100 times N, only this, in this case, P would be 25, depending on if you're trying to find the first quartile. P would be 50 if you were trying to find the second quartile, and P would be 75 if you're trying to find the third quartile. All right, so just understand the relationship between quartiles and percentiles. Okay, so moving on to the next concept, which is the normal distribution. Okay, so let's say you can be happy on a scale of 1 to 10, where down here is 0, here is 5, and here is 10. And this is the happiness level that you are at, or people are at. And this axis represents the number of people at these various levels. Now, the way that data often shakes out in the real world is something like this bell curve deal, all right? And basically what this means is most people are, at a 5 level of happiness, and that would be the mean or the average level of happiness, okay? Whereas you're going to have a few people, not many people, but a few people have an average happiness of 10, and you have some, really, really miserable people over here, and they're sort of few and far between, but most people are sort of like moderately happy. All right, so that's a way of thinking about the bell curve. Now, this could represent anything, usually this is like number of people or number of items or what have you, and this represents some other factor. But anyway, it's often the case that in the real world there is this sort of bell curve where most people line up, right around the middle, all right? Now, that is called a normal distribution. A normal distribution has this bell shape, all right? Now, another thing to take into account is something called standard deviation, which we already sort of discussed before, but standard deviation is really applicable when it comes to the normal distribution. So let's say the standard deviation was 2. Okay, now what that means is 1 standard deviation away from 5, from the mean, would be, 7, right? Because that would be a standard deviation of 2, right? So 2 units in that direction would give you 7. So 1 standard deviation away from the mean or above the mean would be 7, and 1 standard deviation below the mean would be 3, right? So that is how that works. Now, here's the thing. You might end up dealing with something called the standard normal distribution, where you essentially have another bell curve, and this is the standard normal distribution. I'll just write that down. In statistics, you're going to sort of deal with a normal distribution, but then something else called the standard normal distribution, where the mean which is always in the middle, is temporarily called 0, and anything that is 1 standard deviation above the mean gets a score of +1, and anything that is 1 standard deviation below the mean gets a score of -1. Anything that's 2 standard deviations above the mean gets a score of +2, and anything that is 2 standard deviations below the mean gets a score of -2. And these little scores right here, these scores, all right, are called z-scores. Z-scores. Okay, so when you're dealing with the standard normal distribution, you're dealing with z-scores, and z-scores basically tell you how many standard deviations away from the mean do you have. Now, you can oscillate between the sort of regular normal distribution and the standard normal distribution, in the sense that, you know, a mean of 5 here would be corresponding with the z-score of 0. So by the way, the mean of the normal distribution always corresponds with the z-score of 0 when it comes to the standard normal distribution. So 5 corresponds with 0. The number 7, happiness level 7, would correspond with a z-score of 1. And happiness level, let's see, it would be 9 actually. If you were to calculate, you know, another standard deviation, it would be 9 because the standard deviation is 2. So happiness level of 9 would correspond with the z-score of 2. Happiness level of 3 would correspond with the z-score of -1, and so on. Okay, so that's a little bit more information with regards to the normal distribution, and typically the kinds of concepts that might come up when you're dealing with the normal distribution. Okay, so the next concept is counting. What that is pointing to, likely pointing to, is the fundamental counting principle. Fundamental counting principle. And what the fundamental counting principle says, basically, is the following. If I have 12 hats in my closet, 13 pairs of pants, and 5 shirts, how many outfits can I make? Well, you get that by representing the choosing of the hat as an event, denoted by that underline. The choosing of the pants is an event as well, and the choosing of the shirts is an event as well. And basically what you want to do is, you know, we're just going to write H for hat, P for pants, and S for shirt. And if you want to know how many outfits you can make out of, you know, what you have in your closet, well, you just put all the possibilities of what could go there. For example, there are 12 possibilities for hats, there's 13 possibilities for pairs of pants, and there is 5 possibilities for shirts. And all you have to do, according to the fundamental counting principle, if you want to know how many outfits you could make out of all this, instead of counting them, you know, in a tedious manner, you just set this up and multiply all of these. And at the end of the day, you would get a total of 780 outfits. It's a lot of outfits. All right, so that's the fundamental counting principle, which is likely what they mean by counting here. Okay, so now they say permutations. So permutations is how many different, I don't know if it's not really the right word, but you could think of it as how many different orderings there are. That's a good word for it. How many different orderings are there given a particular circumstance? So for example, let's say we have 10 athletes competing, and there are, let's see, there's the gold medal, there's the silver medal, and then there's the bronze medal that you could win, right? And there's 10 athletes competing for all these medals. Well, how many different, you know, winners could we have? Well, this is a situation where actually the order matters. So you could even literally think of it as what they typically have with the platform, right? And basically the order matters because this first highest platform is the gold, the next one is the silver, and the next one is the, we'll use red, that's bronze.
And basically you want to ask yourself, all right, well, how many different orderings could take place if there are 10 athletes competing? 10 athletes competing. Well, how many possibilities are there for the gold medalist? Let's say it's a race. Well, it's, how many possibilities are there for the person who crosses the finish line first, right? Well, clearly that would be 10. There's 10 possibilities. But then once we have a winner here, how many possibilities do we have left for silver? Well, that would be 9. And once we have the silver medal winner, how many possibilities do we have for the bronze medalist? Well, that at that point would be 8. So at this point, you would just multiply 10 times 9 times 8, and that would give you 90 times 8, which is 720. All right, so there are 720 different possible orderings here, okay? Now, the key is with permutations, and I'll just underline what we're talking about. It's permutations. The key is with these is that the order matters. So when it comes to the permutations, order matters, namely gold, silver, bronze in this case. All right, so that's permutations.
Okay, so the next concept is combinations. Combinations is when the order does not matter. All right, so permutations is when the order matters, and combinations is when the order does not matter. And an example of combination problem is something like you have 10 employees, and you want to know how many teams of 3 can you create? How many teams of 3 can you create from 10 employees? How many different teams of 3 can you create? And, imagine that the names of the employees, strangely enough, were A, B, C, and D, dot, dot, dot. And we have 10 of these. Now, what do I mean by the order doesn't matter? What I mean by that is, let's say one of the teams of 3 that you pull from the 10 employees happens to be A, E, and F. Well, does it really matter if we list it like this, or if we list it like this? It does not matter, because this is the exact same team, right? It's still the same 3 people. It's still the same team. So when the order by which you list them does not matter, that's when you want to do combinations. So the question might be, okay, so how do we figure it out? We just did a whole piece on permutations, but what about combinations? How do you figure out the answer to this question? And basically what you have to do is employ a very special formula that would enable you to figure this out. That formula is a little bit clunky. I like to do sort of like a shortcut. And for those of you watching at home, and for those of you who don't really care about doing things the textbook way, but are just more interested in getting the right answer as quickly as possible, I'm going to present to you a shortcut that should work every time when it comes to combination problems. So anyway, the notation would be to do this. You could say 10 over here and 3 down there. So this is how many people are in the population that you're choosing from. This is how many people you're choosing. This is read as 10 choose 3. Now, I'm just going to tell you, this does equal a special kind of formula that, college professors might make you memorize. But I'm going to cut to the chase. What you have to do is you take the bottom number and you find the factorial of the bottom number. And what that means is you exhaust the bottom number as follows. You say 3 times 2 times 1. Okay, you go as far as you need to in this pattern until you reach 1. Now, if this was 4, it would be 4 times 3 times 2 times 1. If it was 7, it would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So you do that first. You actually work with the bottom number first. And then you take note of how many placeholders you have. You could think of these 3 numbers as sort of placeholders for the numerator as well. And there are 3 placeholders. And what you want to do with those placeholders is you begin the process of doing the same thing with 10, only you stop once you've reached the maximum amount of placeholders. You just stop right there. So once again, start with the bottom number, exhaust it with a factorial, 3 times 2 times 1. Take note of how many placeholders you've created. Begin the same process with the top number, only stop once you've reached the maximum placeholders. Now, you could always just plug this into your calculator, although this is pretty easy, that's just 6, and just take it from there, divide the bottom by the top, or divide the top by the bottom, I should say. But I will say that there will always be these convenient cancellations. For example, this 9 and the 3, there's a convenient cancellation there. This 10 and the 2, there is a convenient cancellation there. It's almost always the case, if not always the case, that the bottom could be turned into a 1. And by the way, when you cancel these out, that's just 1 and 1. So it's almost always the case that the bottom could be turned into 1s, a string of 1s being multiplied together due to those convenient cancellations. So now all that's really left to do, since anytime you divide something by 1, it just remains itself. Basically all you have to do is just multiply the top numbers. So it's going to be 5 times 3, which is 15, times 8, which is 120. So that equals 120. So in other words, how many different teams of 3 could we create from 10 employees? Well, that would be 120 different teams of 3 that you could create from 10 employees. That's how you do combinations. Okay, so moving on to the next concept, we have simple probability, sample space, and events. Okay, so simple probability, first of all, it's often denoted by this symbology right here, where the E represents an event. So if you want to know the probability of a particular event occurring, essentially what you're saying is, okay, what is P of E? All right. And typically, that's going to be a matter, or always really, in a sense, it's going to be a matter of the number of possible outcomes in event E, all over the total number of possible outcomes. Okay, so once again, number of possible outcomes in event E over total number of possible outcomes. So for example, imagine we had a problem that said, okay, if you flip a coin 3 times, what are the chances of getting 2 heads and 1 tail? All right. And basically what you want to do, what I would advise is getting clear on this denominator first, the total number of possible outcomes. And basically what that is the sample space. All right, we already kind of talked about events. The event in this case is 2 heads and 1 tail. And the sample space is the total number of possible outcomes. And one way of going about that is to make a tree diagram, which I'm going to demonstrate right now. So a tree diagram takes into account the different things that could happen. So for example, if you're flipping a coin 3 times, clearly there's going to be the first flip, there's going to be the second flip, and there's going to be the third flip. Now, what are the possibilities that could happen on the first flip? Well, either you're going to get a heads or you're going to get a tails, right? Now, let's say you get a heads for the first flip. Well, what are the possibilities for the second flip? Well, then you're either going to get a heads, right, or you're going to get a tails. In this case, what are the possibilities for the second flip? Should you get a tails for the first flip? Well, that would be also the possibility of getting a heads or a tails, and the tree diagram would have you connect these, right? So once again, under the first flip, let's say we get heads. Well, then for the next flip, there's still the possibility of getting either a heads or a tails, right? And then from there, it's going to be flip 3. Well, imagine you got a heads for the first flip, a heads for the second flip. Well, what are the possibilities for flip 3? Well, maybe you would get a heads and a tails again. and that would be connected right here, and similarly it would be heads, tails here as well. So that's the tree diagram. I'm sure a lot of people who are watching are somewhat familiar with this, probably. It's probably something you did maybe when you were younger in math class. It's always a good idea to write everything that has just happened at the tail end. So this one represents 3 heads in a row. This one represents heads, heads, tails, right? This one represents heads, tails, heads. We have heads, tails, tails. We have tails, heads, heads. We have tails, heads, tails. We have tails, tails, heads. And we have tails, tails, tails. Now, that right there, all of this blue stuff, is the sample space. Okay, that is what is referred to as the sample space, because these are all the possible things that could happen if you flip a coin 3 times, and that corresponds with the total number of possible outcomes. So basically what we could do here is we could sort of write that. How many total possible outcomes are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. Right? There's 8 total outcomes, possible outcomes. Now, we want to know what is the number of possible outcomes in event E. In other words, how many of these outcomes are such that there are 2 heads and 1 tail? Well, I see 1 right here, so I'm going to put a little check mark next to it. I see 1 right here. I see 1 right here. I see another 1 right here. And it looks like that is all. So we have 3 out of 8. There are 3 combinations there. So we have 3 over 8. So that would be the answer to this problem. If we want to know what is the probability of getting 2 heads and 1 tail if you flip a coin 3 times, well, that's going to be 3 out of 8. What did we do? We got clear on the sample space first. We got clear on the total number of possible outcomes first. And then we got clear on how many possible outcomes of the actual event that we're analyzing, how many of those exist, and that would be 3. All right, that's how you do that. That is simple probability sample space events. Again, I would recommend, for the most part, if you're dealing with simple probability, start from the bottom up, get clear on the total number of possible outcomes first, get a sense of the sample space first. That tends to make it easier. That's a way of looking at the big picture first and then zeroing in on the details. This numerator has to do with the details, namely the specific event that you're analyzing. Okay, so the next concept is dependence and independence. So that is right here. I'll just do a little asterisk. All right, so dependence and independence. Okay, well, when it comes to probability, dependence and independence refers to whether or not, like, if, you know, let's say you have a bag of marbles. Okay, this is like the classic example. You've got 2 blue marbles, and you've got 3 green, and you've got 1 red marble. And imagine the teacher asks, okay, what's the probability of pulling out 1 green marble and, you know, holding it, not putting it back in the bag, and then immediately after that pulling out a blue marble? Well, that right there is an interesting question, and it really is a great question to highlight the difference between dependent and independent events. So there is the first event of pulling out a green marble, and then there is the second event of pulling out a blue marble. Now, the probability of pulling out a green marble, well, that is definitely going to be 3 out of how many marbles we have in there. So that's 6 total marbles. So there's 6 possibilities, right? There's 6 possibilities of how many marbles you could pull out. And it so happens that 3 of those 6 possibilities happen to be the green marble. So the probability of pulling out a green marble is 3 over 6, also known as 1/2, if we were to reduce it. And then the probability of pulling out a blue marble. Notice how the sample space is lessened now, because we already pulled out a green marble. Imagine, you know, we pulled out this one. Now the sample space
that belongs, that is represented by the denominator here is not 6 anymore. Now it's 5 because there's only 5 marbles left in the bag. And at this point, you have 5 marbles left in the bag. Well, how many of them are blue? Well, that would be 2. All right, so that's 2 out of 5. And by the way, if we wanted to figure out what's the probability of pulling a green marble, keeping it, and then pulling out a blue marble, I just found out the probability of the first thing happening. I found out the probability of the second thing happening after the first thing happens. And then all you have to do is basically multiply the 2 fractions together, and that would give you the answer. And that turns out to be 1/5. There is a 1/5 chance that you will pull out a green marble, keep it, and then pull out a blue marble. All right, so that's how that works. Now, the point is, when it comes to dependence and independence, the probability of pulling out a blue marble was affected by the fact that you pulled out a green marble first, right? So anytime you have a probability of something that is affected by something that you did before, that means that this is a dependent probability. It's a dependent event, we should say. All right, this event is dependent on this one. Now, let's contrast that with an independent scenario. An independent scenario would be if we did not keep the green marble, but we rather replaced the green marble. So imagine we replace the green marble. Well, that changes things. That turns these events into independent events because the probability of pulling out a green marble, well, that's the same in the sense that, let's just make this a green marble again, right there. So the probability of pulling out a green marble is still going to be 1/2, right? Because we have 3 out of 6 total marbles, so that's going to be 1/2. But check it out. We pull out the green marble, and then we put it back in. And then the probability of pulling out a blue marble, guess what? That is going to be a denominator of 6 because there's 6 total marbles in there. So it's going to be 6, not 5. And by the way, it would be 2 over 6, also known as 1/3, after we reduce it. So notice how this event, pulling out a blue marble, that event is unaffected by what came before, because once we pulled out this green marble, we put the green marble back in. So this would be an example of an independent, 2 independent events, because we replaced it, right? And this right here, the previous example, where it's without replacement, that is dependent. Okay, dependent. I'll put these in quotes. I'll put this in quotes. All right, so that is dependent, means that the second event or third event or the subsequent event is affected by what came before. The probability depends on what came before. And independent means the probability of both of these things are treated as separate, independent, isolated entities, because what happened here does not affect this one, namely because we replaced the green marble. Hopefully that makes sense. Okay, so this is going to be the last concept for this video. This is going to be part 1 for the contemporary mathematics concept overview. Expected value is the next concept, so I'm going to put a little asterisk there. Okay, so when it comes to expected value, that's basically the average amount of, maybe the average score over time, or the average amount of points over time. So for example, imagine we had a wheel, like a spinning wheel, like might be at a casino, and there is a 25% chance that you're going to get 10 points, and there is a 75% chance that you are going to get, let's say, 2 points, okay? And imagine you wanted to know, like, okay, well, there's a relatively small chance that I'm going to get 10 points. There's a big chance I'm going to get 2 points when the wheel is spun. So what would be my average amount of points per spin over time? All right, my average amount of points per spin over time. Well, that would be found by analyzing the expected value. So in this case, it would be the expected value of a single, how many points, or we could say the expected value of a single spin in terms of points. Well, all you have to do is multiply the amount of points you would earn times the probability of getting those points. So in this case, the probability would be a 75% chance, also known as 0.75. So when you're doing these calculations, you might want to turn it into decimals. So that is, one possibility of getting 2 points is a 75% chance of getting that. And then what you're going to do is you're going to add that to the probability of getting 10 points. So we have 10 points here, and we have the probability of getting 10 points. In this case, it's 25%. So in other words, we have points and we have the probability of getting each point. All right, and the probabilities are here and here, and the points are here and here. Okay, so that is how to figure out the expected value. And in this case, 2 times 0.75 is 1.5. 2 times 0.75 is 1.5. So we're going to write that right now. 1.5, and that's going to be added to 10 times 0.25, which is really 2.5. And when I add those together, I'm going to get 4. So what this means is, it's like, even though it's impossible to score 4 on a single spin, let's say you spin the wheel an infinite amount of times, right? The average amount of points per skin that you will get after spinning this an infinite amount of times is 4 points per skin, per spin. That is the average amount of points you're going to earn per spin if you spin this wheel. Okay? And once again, understand the expected value. It doesn't necessarily represent like what you would get on a spin. It just means what the average would be given a long enough period of time and given enough spins of the wheel. What would the average point per spin be? All right, so hopefully that makes sense too. There will be another video or two to get to the rest of the concepts, but for now, I hope this was helpful, and I will see you soon. If you have questions, list them below, and I will get to you as soon as I can.